Hello, good morning and good afternoon for everyone. Welcome to the first session of the Climbing and Walking Robots Conference. My name is José Lima and I will share this session. This session is titled M1, Modeling and Simulation of Climbing and Walking Robots first. I kindly ask all the people presented to mute yourself and stop the video during the presentations. And at the end of each presentation, if you have any question, please write, I have a question on the chat. In this session, we will have four papers. The first one is titled ClimbLab, MATLAB Simulation Platform for Legged Climbing Robots, and it will be presented by Kentaro Uno. So please go ahead.
So thank you very much for the kind introduction. I think I could share my screen. Can you see my screen and hear me well?
Yes, perfect.
Okay, thank you very much. So hello and nice to meet you all. This is Kentaro Uno speaking from Space Robotics Lab at Tohoku University, Japan. Today, I'd like to introduce our up-to-date development of the MATLAB simulation platform dedicatedly designed for the legged climbing robotics. Now, legged climbing robots would be the key technology to expand the mobile robots exploration coverage and the application fields of the legged robots. However, it is generally not simple to perform experiments with climbing robots because of the difficulties accessing harsh natural terrain. In addition, field testing campaigns for these climbing robots often requires large-scale equipments to ensure the safety of the robot and operators. And these safety tools, such as the gimbals and the safety ropes, would interfere the robot behavior. On the other hand, some experimental validation can be performed in the indoor test field. Iterative testing in the indoor controlled environment is also essential in terms of the reproducibility and safety than the outdoor testing in natural terrain. However, this kind of test bench has the limited workspace that the type of the experiment is constrained. There should be the trade-off between the safety and reality for the mobile robot experiments, particularly in case the robot is deployed in such an extreme environment. In developing such a robots that must work with high reliability in a harsh environment, simulation-based study plays an essential role. Particularly in the design phase, preliminary simulation analysis gives us a fundamental mechanical requirements to decide link geometries, mass distribution, and actuator selection. Also, in the validation phase, simulation in severe or high-risk situations is quite important to investigate the climbing performance without any physical risks before real-world deployment. Our research group has been building the simulation platform in the project to develop the legged climbing robots towards the extreme environment exploration named ClimbLab. ClimbLab is a standalone simulator dedicatedly designed for the legged robots working and climbing. And basically the user do not need any additional toolboxes. ClimbLab has many functions that is uniquely useful for climbing robotics. For example, equilibrium-based tumble stability criterion evaluation, the demonstration of the gripping force and gripping state evaluation. Also in this simulation development, as a main policy, we have been focused on the simplicity and modularization in the code. All the modules illustrated in the right-hand side figures are organized as modules with the simple subroutine functions. I believe this code style would be useful for the user, especially to begin the research and development of such mobile robots with the complex system. Let me go on to the ClimbLab's available functions in detail. ClimbLab has all essential modules necessary for climbing robotics. Any robot models are designed as articulated system. The simulation world is also customizable by changing terrain shape, inclination, ground stiffness, and gravity. Various working gait strategies can be built by changing the modules of swinging limb selection, foothold selection, and baseball planning, and so on. Of course, the user can implement your own motion planner in the module with ease. ClimbLab simulator employs only one single toolbox named SpaceDyn for rigid body dynamics computation, which was also developed and is maintained by the same authors. SpaceDyn module is also automatically installed with ClimbLab. ClimbLab's visualization modules enables to log and plot all the variables and make an animation of the robot behavior so that the user can smoothly perform the detailed analysis. In this slide, let me briefly present the simulation flow of the ClimbLab. ClimbLab's each computational phase is composed of the group of subroutine functions. First of all, various parameters are defined according to some preset files or manual settings by the user in advance. Then, at the beginning of the main simulation loop, information from the surface is obtained, as it would be on an actual robot collecting point cloud data from a camera. This module is useful to simulate the robot's vision sensors. In the next locomotion planning modules, the robot working gait is planned, and by solving inverse kinematics and dynamics, the necessary state variables, such as joint angular positions, are updated at each moment. Subsequently, dynamics and static equilibrium of the robot is computed in order to evaluate the robot stability, considering the robot pose, gravity and acceleration effects, and gripping force. In this module, several stability margins are calculated. Next, the input signals of the actuator of the simulated robot is calculated to achieve the desired joint position. In the following modules, the physics engine calculation is performed. This module includes the gripping state evaluation. Then, based on the physics calculation, the robot pose is updated. This main loop calculation is updated at a rate with 1000 Hz as a default settings until the simulation is finished. From now on, I'd like to show some simulation examples by ClimbLab simulators. In this simulation, a quadrupedal robot have robot supporting the body with the grippers on overhanging wall under Earth's gravity. The robot mass is 2.4 kilograms, and the gripper that performs 13 Newton of holding force is assumed. As you can see in this comparison, the assumed climbing robot Haburobo can hold the body on the cliff that has the 10 degrees overhanging inclination from the vertical wall. However, in the right-hand side video, with more additional 10 degrees inclination, it fails. Focusing on the robot behavior, the upper grippers detach it first, and finally, all the foot lose the contact from the ground. This behavior can be explained in the right illustration. For the robot climbing on the wall, the face-up moment is acted by the gravity. As a result of this, the direction of the reaction force acting on the feet are opposite between the upper feet and lower feet. If the reaction force acting on the upper feet becomes larger than the gripper's endurable force, the upper feet loses the ground contact. From this simulation animation, we can see that the ClimbLab can demonstrate this physics reasonably. In this slide, in this next simulation case, first I'm showing the simulation of the robot climbing on the flat ground with the conventional crawl gait. In this simulation, the robot climbs on the slope successfully, thanks to the sufficient gripping force. However, it is important to note that this simulation assumes that the robot can grasp any point on the ground. In contrast, for the irregular terrain climbing, the graspable points are discretely given. In this simulation, the graspable points in the swinging legs workspace are detected at the summit of the convexities, shown as the green dots. And the used gait planner in this simulation choose the optimal leg and its footholds step by step. This type of non-periodic non-gated working sequence is necessary, particularly for the rough terrain climbing locomotion. In the next case, for the climbing on the steep slope, if the robot keeps the natural stance, the higher base position leads the larger face-up moment, which might decrease the stability. To avoid this, the stability area stance is proposed. That is to lower and lean forward the base position to the slope so that the tumbling moment is minimized. In this simulation, standard stance and the stability area stance is compared by making animal B robot model climbs on the steep slope. By analyzing the time plot of the tumble stability margin and the joint torque consumptions, the stability area stance achieves higher stability and less energy consumption compared to the standard stance. As shown in this simulation analysis, we can see that the ClimbLab's capability to evaluate the climbing robot's performance like this. As a last example, we imported the pre-scanned terrain map into the ClimbLab framework and ran the robotic climbing simulation using this map. ClimbLab is capable of importing any 3D point cloud data format to handle the terrain information. These are the simulation results, assuming the robot climbing on the pre-scanned terrain map. As you can see, the robot successfully climbs the more realistic steep irregular terrain. In this simulation, the robot is finding the graspable convexities, selecting the optimal footholds, and adapting the base ports to sustain the stability. Even the inclination of the terrain is completely vertical. The simulation succeeded. Just before going to the summary of my talk, I'd like to use this opportunity to mention that ClimbLab has been already open sourced. The GitHub URL can be found in our paper as well. Also, I will have another talk in this conference tomorrow. So if you are interested in, I'm happy to see you again in the tomorrow's sessions. Then I'd like to conclude this talk. Simulation study is essential for the mobile robots that is particularly works in the extreme environment. And we developed a MATLAB-based framework to simulate and analyze leg climbing robot dynamics named ClimbLab. I introduced many simulation examples in this talk, and if you are interested in using this simulator, please go to our GitHub page. It is already open sourced. Thank you very much for your attention. I'm happy to answer your questions.
Okay, thank you very much for your presentation. Are there any questions from the audience?
Yes, it's Clive Lockham here. I'd like to ask a question, if I may.
Yes, of course, please.
Sure.
Hi, Kentaro. Very interesting presentation. Thank you very much.
Thank you very much.
One thing I really have sort of two questions. One is, is the system specifically for four-legged robots, or can it also be used with robots with more or less legs? And the other thing was whether the terrain can include disturbances, such as a rock moving when force is applied to it. I was wondering what your thoughts are in that area.
Thank you very much for asking the question. As for the first questions, it's totally possible to simulate any number of legs systems. So actually in ClimbLab, we can design any type of the robot as a one link parameters file. So in that file, we can design the robot as a link tree, as a tree system. So you can just select the number of limb and design any link configurations as link trees that is well known to define the robot parameters. So it's totally possible to design the less limbed robot and more numbers of them. And as for the second questions, right now, in the current ClimbLab simulation architecture, it's not possible to simulate any other like obstacles like falling log or something like this. Right now, it's all the world is really static. Just import as the static terrain, and only one movable object is the robot. But it's very useful to simulate multiple objects in one simulation. And I will consider that possibility with my students. And maybe in the near future, we will update these functions.
Very good. Thank you very much.
Thank you very much.
Okay, thank you. Well, it was a very interesting work, but we think that we need to go further for the next presentation. So thank you very much, Kentaro, for your presentation.